Hello. Now, by popular demand, there will be a video on writing up this lab, the hydrogen spectra of hydrogen. While I'm doing this video, I'm watching the baseball game. The Dodgers are winning 7-3. Go Dodgers. Yep, San Francisco's losing. Yes. Anyway, that's enough of that. Okay, so what do we have? Well, this is the same kind of write-ups as we've done for the previous labs, individual labs. You're going to have the same kind of sections. You have objective, theory, procedure, data, and conclusion. Alright, let's go over these one at a time here. The objective. Before I do, though, let me just remind you that there are two documents I put, supplementary material I put. There's on the File Depot, and you can get to them from the class homepage. And it's just supplementary or something like that. There's two really good documents about all this stuff, and you can probably get almost everything you need off of them. Alright, so make sure you go see those. So what are we trying to do? What is the objective of this experiment? Well, what we have is we are getting the, we have hydrogen tubes, and we're getting it to emit light. Well, that light can be broken up into different parts that we could combine up, and that's what we actually see. Alright? But by putting it through the grating, or you could also do it through a prism, but we're going to use a grating, because that's great. Okay, that was funny. So we're going to use a diffraction grating. This isn't going as good. And we're going to measure the wavelengths of the lights. What happened here? Oh, 7-5. What Dodgers are still ahead? Okay. So, how does that happen? Well, if you look at some of these charts in these documents that I'm referring to, alright, they show you how when electrons in the hydrogen atom transition from one state to another, alright, they give out different wavelengths of light. Now, for hydrogen, some of those are infrared, and some of those are ultraviolet. We can't see those, so we don't care about them. The only ones we care about are the visible ones, which are also called the Balmer series ones. And you can see they're in the middle right there. Not too high, not too low. Alright? So, what does that mean? So our objective is to find out what the, if we can find out what the wavelengths of that light is, we can use that E equals hc over lambda equation to measure, experimentally measure the amount of energy in joules. It comes out in joules, and we can compare that with the theoretical values and determine if we can accurately measure these electron transitions. Okay. What's the theory behind all this? Well, the theory goes into something called quantum physics. Let me get out my quantum physics book. Oh God, this thing's heavy. Wow. I haven't pulled this book out since sophomore year. You want to do all this? I don't think so. I don't either. Let's put that back. Alright, let's just make it a little bit easier. If you read over the document there, it talks about the Bohr model of the atom. Now, the Bohr model of the atom says that you have these discrete levels of energy for electrons. You know, 1, 2, 3, 4. By the way, my favorite color is 4. Some of you probably didn't get that, but if you were there for that part of the lab, you were probably laughing. Okay, so my favorite color is 4. What's your favorite color? So anyway, where was I? Now, the interesting thing about it is the Bohr model of the atom really only works all the time for hydrogen. And there's some statistics that go on with that. Interestingly enough, Einstein himself didn't believe it because of the statistics involved, but it turned out to be right. So if you read over this document here, it'll talk about the Bohr model of the atom. I don't want you to get into detailed explanation of quantum mechanics. I really don't. But what you want to do is figure out that, what you want to demonstrate is that you understand the Bohr model of the atom and how when an electron transitions from one energy state to another, it's going to give off energy. The energy is in the form of light. The light is going to have a wavelength equal to blank. All right, and then you can also figure it out from that equation that we have, that E is equal to 13.6 times 1 over 2 squared minus 1 over n squared, something like that. I can't remember the exact equation. And just talk about that. This one will have not a lot of equations, just a couple really. And I won't spend more than somewhere between a half and 2/3 of a page writing about the theory. Maybe a page if you're getting really ambitious, but I really don't want to read it. Procedure. Procedure, just reference the lab manual. Data. You have your data sheets. Just include those. That's easy. Conclusion. Now this is really going to be determined by how accurate your data is. Alright? So, did you get good data? Well, did you? Did you? I think you probably did. Okay. Now, what are the sources of error? Well, let's think about that one for a minute here. What could we have screwed up in that lab? Oh, gee. Let's see. We're taking the data in the dark. We're trying to read something that was about yay big. All right. The diffraction grating on a lot of these things couldn't be held at a 90-degree angle relative to the eyepiece. I mean, come on. If you can't think of a bunch of potential sources of error, you must not have been there. Were you there? I was there. And that's about it, really. So remember, I mean, the only hard part in this is the theory, and if you summarize what you see in in the documents I posted, you're probably going to do just fine. So I'll see you in the physics lab.